Today we're going to be talking about the derivatives of exponential functions. So we're going to find a formula for the derivative of a to the x. Before we do that, we're going to investigate e to the x. So I'm actually going to do this in the calculator. So in the calculator, in y1, I'm going to do e to the x. In the second one, we're going to do the derivative of y1. So there's our shortcut menus. First shortcut menu is F2, gets us our derivative. So we have dx of y1, or you can just type in e to the x again. So the shortcut for the y's are under the F4. And then we're going to do is x equals x. And then we will graph. There's e to the x. And here comes its derivative, which, ta-da, is the same thing. So the derivative of e to the x is e. So e to the x prime is equal to e to the x. I will include a link to a derivation for this so you can see, if you want to, algebraically where this comes from. But for right now, we're just gonna, I hope you will be okay with the graph telling us that the derivative of e to the x is e to the x. We can then use that to find the derivative for a to the x. So I will go ahead and derive this one. I'm going to rewrite this as e to the natural log of a to the x. So e to the natural log, that would cancel, but we're introducing that for this derivation. This allows me to use the power property, which says e makes it x natural log of a. So we went through all those logarithm rules last time. And now I'm going to take the derivative. So the derivative of e to the x is e to the x. So this is going to be e to the x natural log of a times the derivative of the inside function here, which is going to be x natural log of a. So that's just going to be natural log of a. And then we'll work backwards. So we'll put the x back up here, so e to the natural log of a to the x times the natural log of a, ln a. The e to the natural log cancel, so this is going to end up being a to the x times the natural log of a. So our first derivative is e to the x prime is e to the x. A to the x prime is going to be a to the x times the natural log of a. So here's my big master list of derivatives that we have. I'm going to add to this. So last class we did natural log and log base a. Now we're going to do e to the x, which is e to the x, and a to the x, which is going to be a to the x natural log of a. So now we will use those to do some derivatives. So the derivative of e to the x, y prime, is e to the x. Here, if I have e to the negative x, we're going to have e to the negative x times the derivative of negative x, which is negative 1. So this is just going to be negative e to the negative x. This one, I'm going to leave a space here again, is going to be e to the 7x times the derivative of 7x, which is 7. So we can generalize that the derivative of anything e to the ax is going to be a e to the ax. Here, I want a formula for the nth derivative of e to the 2x. So let's take some derivatives and see what happens. So y is e to the 2x, which means y prime is going to be 2e to the 2x. If I take that derivative again, we're going to have 2e to the 2x times 2. So we'll have 4e to the 2x. We do this again, we're going to end up with 4e to the 2x times 2. So that's 8e to the 2x. That was our triple prime. So the only thing that's changing is this number out front. And if we look at the relationship between what derivative we're taking and what's out front, first derivative is 2, second derivative is 4, third derivative is 8. And what we ended up doing here was just taking, multiplying by 2 again. So the nth derivative this number is going to be 2 to the power of whatever derivative we're taking times e to the 2x. These next couple, we're just going to apply the chain rule, so deciding which is the inside function and which is the outside function. So outside here is e to the x, so this is going to be e to the 1 over x times the derivative of the inside function, 1 over x, which is going to be negative 1 over x squared. Here, my outside function is sine, my inside function is e to the x. So my derivative is going to be derivative of sine is cosine e to the x times the derivative of e to the x, which is e to the x. Here, my outside function is the e, the inside function is cosine. So this derivative is going to be e to the cosine of x times the derivative of cosine, which is negative sine x. For number 9, our derivative is going to be, again, chain rule. So the outside derivative is just e to the x cosine x times the derivative of the inside here. And the derivative of our inside function is a product. So we're going to have x prime times cosine of x plus the derivative of cosine times x. So this is going to be e x cosine x. Derivative of x is 1, so we're going to have cosine of x. Derivative of cosine is a negative sine of x times x, and you could always move that out front. Next one on the page is going to be a quotient. So our derivative is going to be the derivative of the top times the bottom minus the derivative of the bottom times the top all over the denominator squared. So the derivative of e to the x is, again, e to the x, natural log x. Derivative of natural log is 1 over x times e to the x. All of that over natural log of x squared. Last one on this page is, again, a composition of functions, this time 3. So we have an outside, which is natural log, the middle, which is cosine, and the inside, which is e to the x. So we'll just start on the outside and work our way in. So the first one is natural log, so that derivative is 1 over x. So this is going to be 1 over cosine e to the x times the derivative of our middle is cosine, so that's going to be negative sine e to the x times the derivative of e to the x, which is e to the x. Okay. On the next page, this funny looking equation is actually a hyperbolic trig function, which you don't necessarily need to know to complete this problem, but that's what this is. So we are going to use the quotient rule here. So this is going to take up some room. So we're going to have the derivative of the top times the bottom minus the derivative of the bottom times the top okay, all of this over the denominator squared. Okay, so we'll do these derivatives. So this one's derivative is going to be e to the x. Derivative of e to the negative x is going to be negative e to the negative x. Here we're going to have e to the x plus e to the negative x. All of that over e to the x minus e to the negative x squared. Okay, you can stop here. I am gonna go ahead and continue to simplify this one because it does simplify down pretty good. So we're gonna FOIL each of these sets. So when we FOIL, we're doing e to the x times e to the x, which is going to be e to the 2x, e to the x minus a negative e to the negative x. So when we multiply with the same base, we're adding the exponents. So this is going to be minus e. If I add x and negative x, I get 0. And then a negative e to the x times a negative e to the negative x is going to be a positive e to the negative 2x. This is going to be minus e to the x times e to the x is e to the 2x. So all of these are going to be positive when I FOIL it, so when I distribute through the negative, they're all going to be negative. So e to the x times e to the negative 2x is e to the 0. So we're going to subtract e to the 0. And then e to the negative x times e to the negative x is e to the negative 2x. So we're going to have a minus e to the negative 2x. All right, so let's look at what happens here. Sorry guys. In my foiling, I skipped. So when we multiply this one and this one, we get e to the 0. So we actually have 2 e to the 0 here, and same there. So look at what we have. We have an e to the 2x minus an e to the 2x. We have an e to the negative 2x minus, so we have a positive and a negative of the same thing. So that leaves me with negative 2 e to the 0. E to the 0 is 1, minus another e to e to the 0. So we have a negative 2 minus 2, which gives me negative 4 out of all of that equals negative 4. over e to the x minus e to the negative x squared. Again, you don't have to simplify it like that, but just showing that it does there. Okay. At first glance here, you might see this as a chain rule, but be careful when you see e and natural log in the same problem. There's a chance you may be able to simplify it, and here we can, because e to the natural log of x cubed minus x is just x cubed minus x, so that derivative is just 3x squared minus 1. So those were all problems involving e. Now we're going to look at a problem if the base is not e. So just using our rule, the derivative is going to be 2 to the x times the natural log of 2. 10 to the x is going to be 10 to the x times the natural log of 10. Pi to the x is going to be pi to the x times the natural log of pi. X to the pi is not an exponential function. It is a polynomial function. So this one's derivative is going to be followed the power rule. So we're going to multiply down the pi, x to the pi minus 1. So there is a difference between an exponential and a polynomial, which we will visit very soon. So let's just do one more here with the chain rule involved. So this is going to be square root of 2 to the x natural log of x times the natural log of root 2 times the derivative of the inside, which in this case is x natural log of x. So that's going to be x prime natural log of x plus natural log of x prime times x. So this is going to be root 2 x natural log x natural log root 2, and then on the inside 1 times natural log of x plus natural log of x derivative is 1 over x times x, which you could take it a step further and simplify that to 1 if you would like. So these two problems here, this one was an exponential, this one was a polynomial. So what's this? X to the x. Do we use the power rule? Do we use the exponential rule? The issue is it is not either of those. So what we need to do is rewrite this equation, and we're going to use the fact that logarithms allow us to deal with exponents. So in this problem, the first thing I'm going to do is take the natural log of both sides. That allows me to multiply this down, and I'm going to take this derivative implicitly, okay, because I have a natural, if it was just y, then we're good, but since we have the natural log of y, we're going to have to take the implicit derivative here. So the derivative of natural log of y is going to be 1 over y times the derivative of y, which I'm just going to call y prime, equals, on this side of the equation, we're going to need to do the product rule. So x natural log x, and we already did it, so if you just want to cheat and look at that, but I'll do it again. Okay, so there's my product rule. I'm running out of space here, so I'm just going to go up over here. So I'm going to leave this alone for now. So 1 over y times, I'll go ahead and replace that with dy dx, equals 1 natural log of x plus 1 over x times x. So I'm going to have dy dx equals, I'm going to do two things in this step. First thing I'm going to do is simplify that. So that's going to be natural log of x plus 1. And then I'm going to multiply over the y. But my original equation was all in terms of x, so I want that back again. So y is x to the x. So my final answer here is going to be natural log of x plus 1 x to the x. Now, a note on notation. I tend to do this in my first step just so I know I need to replace it with dy dx. But you can leave it as y prime, you can do dy dx, just as long as you know when you're taking the derivative of a function with respect to y that we have to do the chain rule, because the derivative of y with respect to, the derivative of y with respect to x is dy dx. So this process, where we had an x to the x, we call this logarithmic differentiation. So we use logs to deal with something that if the base and the exponent both contain an x, we can use logs to simplify that. So we're going to do the same thing in the next problem. Okay, we have a function that has a base that involves an x and an exponent that involves an x. So we're going to take the natural log of both sides. Which allows me to get the exponent to no longer be an exponent. And now we have something that we can take the derivative of using product rule and chain rule and all of our rules. So here, derivative of natural log of y is 1 over y dy dx. Here we're going to do a product. And again, the notation, do what makes sense for you. So 1 over x prime, natural log 1 plus x, plus natural log 1 plus x prime times 1 over x. So we're going to have 1 over y dy dx. Derivative of 1 over x is negative 1 over x squared. Derivative of this is going to be 1 over 1 plus x times the derivative of 1 plus x, which is just 1. So times 1 over x. The last step then is to multiply over the y in this case being 1 plus x over 1 plus x to the 1 over x. So this final derivative is going to be negative 1 over x squared, natural log 1 plus x, plus, and you can multiply these together if you want to, all of that times y, which is really 1 plus x to the 1 over x. So anytime you have the base and the exponent both containing x's, we use logarithmic differentiation. Here I have the x as the base of the logarithm. So I'm going to change this form. So thinking back to pre-calc, thinking back to algebra 2 even, the base, switching the forms, the base of the log is the base of the exponent. So this is x to the y is equal to e. Well now, did that make it any simpler? Not yet. But good old natural log will save us. So we have natural log of x to the y equals natural log of e. Natural log of e is just 1. So y natural log of x equals 1, which means y equals 1 over natural log of x when I divide. So I haven't done the derivative. All I've done is rearrange this so that I can take the derivative. Now we'll take the derivative. I'll use the reciprocal rule. So the reciprocal rule is negative derivative of that reciprocal over whatever the denominator is squared. The alternative, which is totally acceptable, is to rewrite this as natural log of x, the whole thing, to the -1, and you'd get the same thing. So this derivative is going to be negative 1 over x over natural log of x squared. All right, so now we have a banking problem. So when Max Damone, yes, you may laugh, started high school, his parents invested $10,000 into a savings account to help him pay for his college education. Exactly 4 years later, when he graduated, the account had $15,528.08 in it. Max knows that since the account pays interest compounded continuously, the general equation, m of t, in number of dollars in t years is m of t equals ae to the kt. So that's a formula we used a lot in pre-calculus. A and k stand for constants, and e is the base of natural logarithms. So what we're going to do, and this is nothing new, is we're going to use our 2 points to find our values of a and k. So the 2 points are the 2 times and the 2 monies. So we know at time 0 we have $10,000, and at time 4 we have $15,528.08. So we're going to use these to find a and k in this equation. So I'm going to start with 0, 10,000. So my equation, 10,000, is going to equal a, which we don't know, e to the k, which we don't know, but our time is going to be 0. Well, e to the 0 is just 1, so our a is 10,000. So now we can use that and our second coordinate to find our k. So 15528.08 is equal to 10,000. E, k we don't know, but t we do, is 4. Now we're going to solve for k. So there's no calculus involved here. This is just algebra. So first we're going to divide. That equals e to the 4k. To get rid of the e to the 4k, we take the natural log of both sides. So that gets rid of the e entirely. So then we have 4. So my k is going to be all of this divided by 4. Now, we're going to be using this value in follow-up questions. College Board requires calculator accuracy, which means we can't just round this off if we're using it again. So a trick is to store it in your calculator. Okay, so I'm going to take natural log of 15528.08 divided by 10,000 divided by 4. There's that number, so it's approximately 0.110, but we can't use 0.110, we need to use the whole thing. So what we're going to do is I'm going to store this. Okay, down here at the bottom, you have a little STO and an arrow. So I'm just going to press that. So it's going to take the answer that I just got and store it in, I can choose where. I'm going to go to alpha, and I'm going to go ahead and just make it k. So now k, if I type k into the calculator, and hit enter, the value that I just got is stored in k. So any calculation I have, this is k. So in my equations, I'm just going to use k. I'm not going to write this whole thing out, and I'm not going to use 0.110 because that's not accurate enough. So our general equation here is going to be that I'm going to use is m of t is equal to 10,000 e to the k that we stored times t, where k is this whole thing. That's k. So now we're going to use these to find different values. Okay, so it says that what instantaneous rate is the amount of Max's account changing when the money was first invested at t equals 0. So let's take the derivative of this whole thing. Okay, that derivative is going to be 10,000 times e to the kt times k, using the chain rule. So now m prime of 0 is going to be 10,000 e to the k times 0 times k. So in the calculator, we're going to do 10,000. E to the 0 is just 1. If you want to type that in, you can. But I'm going to multiply that by k. So this is going to be 1100.162. This is the rate of change. So instantaneous rate of change, derivative, is going to be in dollars per day. Sorry, per year. So that means when they first started, he was getting about $1,000 more each year. What about at 4? So that's going to be 10,000 e to the k times 4 times k. Again, k is that stored value. Use the calculator. 10,000 e to the k times 4 times k. We get 1708.341. Dollars per year. So in 4 years, he's getting about $1,700 per year. For C, find the rate of change of Max's money as a percentage of the amount in the account. Okay, so we're going to do the amount at 0, or the rate of change. So what percent of the 10,000 is that? Calculator, 1100.162 divided by 10,000 gets us 0.1100. Then we'll do 1708.341 out of the amount at that point in time, which was 15528.08. Calculator. Which gets us 0.1100 again. So what do we notice about the two answers? Well, they're the same. Okay, so now we're going to show why are they the same algebraically. So we're going to say if our function is this, then this is a constant. So we're doing this in general. So our derivative from up here, m prime of t, is 10,000 e to the kt times k over our whole function way up here, which is 10,000 e to the kt. Okay, so this and this cancel, which is just k, and k is that 0.1100. So these X questions, they're not really necessarily calculus questions, so you might just want to get the answers from the PDF or try them yourself, but I'll go through them quickly. So it's suppose he gets a scholarship and is able to leave the money in the account until he graduates at 8 years. How much money will he have? So M of 8 is 10,000 e to the k times 8, which you can type in the calculator. You'll get 24,112. So that money has grown pretty significantly if we started with 10,000. Max anticipates getting a good job after college and wants to keep the money in the savings account until he retires at 50. So we're plugging in 50 into our equation. And what do we get? A shocking $2,448,905.34. So 50 years of compounded interest adds up quite quickly. How long does it take for it to double? So if we're starting with 10,000, that means we end up with 20,000. So 2 equals e to the kt, so natural log of 2 equals kt. So our t is the natural log of 2 divided by k, which is, if you put it in the calculator, approximately 6.3 years. And then what is the instantaneous rate of change, aka derivative, of Max's money at that time? M prime of 6.3 is 10,000 e to the kt, okay, 6.3 times k, which is $2,200.226 per year. One final problem. A particle moves on the x-axis so that its position is given by x of t equals 4t e to the 2t. What is the velocity at time 3? So we're going to take the derivative. So v of t, we're going to do a product rule here. So this is going to be 4t prime times e to the negative 2t plus e to the negative 2t prime times 4t. So this is going to be 4e to the negative 2t. Derivative here, so this is going to be e to the negative 2t times the negative 2. I am going to evaluate this, so I'll simplify it one step first. So 4t makes this negative 8e to the negative 2, 8t. And then we'll go ahead and evaluate at 3. It's going to be 4e, negative 2 times 3 is going to be a negative 6 minus 8 times 6 e to the negative 6. So we have 4e to the negative 6 minus that was 3. 8 times 3 is 24, e to the negative 6. Add those together, we get negative 20 e to the negative 6. Find our correct answer and circle it. So that is exponentials. Remember, derivative of e to the x is e to the x.